An ideal vapor compression refrigeration cycle with ammonia as the working fluid has an evaporator temperature of -20 degrees Celsius and a condenser pressure of 12 bar. Saturated vapor enters the compressor and saturated liquid exits the condenser. The mass flow rate of the refrigerant is 3 kilograms per minute. Determine the coefficient of performance and refrigeration capacity in tons. Since we have an ideal vapor compression refrigeration cycle, there's going to be a condenser, a compressor, an evaporator, and a throttling valve. We're going to have Q in, Q in from the cold, and Q out. And so now we can fix our states. So we know that there are 4 states, so we're going to go ahead and start by solving state 1. And we have temperature, pressure, enthalpy, and entropy. T1 is -20 degrees Celsius, so you're going to go to your ammonia table and you're going to get your values for H, which is 1. And S is going to be 5.6144, and H is in kilojoules per kilogram. S is in kilojoules per kilogram Kelvin. And we know that across the compressor, state 1 and state 2 is isentropic, so S1 is equal to S2. Because this is S1 is equal to S2. So now that you know that S1 is equal to S2, you're going to go to your ammonia tables at 12 bar, because that is given. And you're going to interpolate your S value to get your H value, which ends up being 1689.5. So now that state 2 is fixed, we can move on to state 3, which it was given in the problem that it was saturated liquid. And P2 is equal to P3. So at state 3, it's going to be 12 bar. And it's saturated liquid, so you can grab your states from your tables, and H3 is going to be 327.01. And across a throttling valve, H3 is equal to H4, so this is also going to be 327.01. So now that all of our states are found, we can solve for A, which it asks for us to solve for the coefficient of performance, and that of a refrigeration, it's going to be beta is equal to Q over work of the cycle, which, looking at our diagram, we know that Q in from the cold is going to be H1 minus H4 over the work of the cycle is going to be H H2 minus H1 because the work is coming in through the compressor. And you're just going to plug in values from your table, and you should get, after calculating, you should get 4.02. The next thing we have to solve for is the refrigerating capacity, and they want it in tons. So we're going to have to use the mass flow rate to solve for part B, which the mass flow rate is given. At the beginning, they give us m dot is equal to 3 kilograms per minute. So since that's given, we can plug this into the formula of Qn is equal to m dot H1 minus H4, and that is how you find the refrigerating capacity. And so you're going to grab H1 and H4 from your table and plug them into your equation, which is going to be Qn is equal to 3 kilograms per minute times 1470.79 minus 327.01 kilojoules per kilogram. And in 1 ton, there is 211 kilojoules per minute. So kilograms and kilograms, kilojoules, minutes, and minutes cancel, so then you're left with tons. And Qn gives you 15.5 tons.